Good afternoon, everybody. My name's Miles Ward. I'm a solutions architect at Amazon Web Services. What I'm hoping to cover today in hopefully some familiar terms, maybe a couple of new ideas, are approaches on AWS, the Web Services platform for cloud, as well as RightScale's extended cloud platform management service. Approaches for high availability, disaster recovery, and fault tolerance in infrastructure. I've been with Amazon Web Services for 3 years, helped design some very large scale infrastructure systems and solutions, and so we'll hopefully be able to go through some of the basic best practices and patterns for high availability and disaster recovery, as well as field as many questions as I can. I'm hoping this thing is deeply informal. Right now we are all sitting quietly and being happy and taking notes. If you have any questions at all, you want to interrupt. If you think what I've just said is silly and you don't agree with it, let's go. I'd much prefer to have this be an active interaction. So a couple of sort of early level setting, some kind of basic terminology pieces that I think will make the discussion a little easier to get through. And then our basic building blocks, the components that we see used over and over again, the patterns that have proven in thousands and tens of thousands and hundreds of thousands of implementations to work how they're supposed to. And then the design steps that you can take in your applications to benefit not only from the kind of distinct value of cloud for this kind of workload, as well as taking advantage of some topologies that may be difficult or impossible in static infrastructure. So what breaks? Why are we doing all this fault tolerance stuff? The list is very long. Your facilities can fail. The services that power those facilities can fail, like power and cooling and floods and earthquakes and lizard monsters from the sea and who knows what. Hardware dies. Your best engineer could decide that computer is the one he hates and he can destroy it with a shotgun. There's every conceivable type of networking failure. Routers can flip bits and you can have every other kind of problem at the code tier. All the software could be written by weirdos and not work how it's supposed to. And those weirdos themselves can cause all sorts of challenges. I have certainly been the one who has poked the button and made stuff not work. So if there are exposures for fault at each of the different tiers of your stack, what do you do? How do you get to a place where, given the highly competitive, highly availability sensitive business market that we all operate in, our customers want the services that they consume from us to work and work every time and work consistently. So if you're building those systems out of these clearly failable building blocks, how do you do? A big concept to internalize, and I think there are a lot of business owners that have heard that there's this little high availability checkbox. Maybe they can check that box, and then this other disaster recovery checkbox. If they check that one, it means that the customers are never unhappy. Fault tolerance and fault independence and high availability design is a practice of risk mitigation, a practice of risk reduction, of identifying the places that are most likely or that would cause the most catastrophic kinds of failures, and creating mitigations and battle plans and practices and automation that defend against those things. It's not a binary step. In every one of these cases, you're going to build something that's more secure and more available and more fault tolerant, not perfectly fault tolerant and perfectly available. And so for every business and every enterprise that runs on a cloud infrastructure, it's critical to identify the real relative value of those applications. What are you willing to invest not only in technology and software and application management, but also in people time and sort of problem solving and the creative analysis of what resources you have available to figure out how you reduce risk as much as possible. If you think about those processes, it's almost impossible without very, very sophisticated human process management to have this stuff work as fast as our customers want it to work without there being automation in place. I just can't run down the hall with the screwdriver fast enough, right? It's too slow in almost every case to have humans do it, and it's also too late to test those practices if it's the very first time that you've ever used them when something fails. So we really don't think of something as fault tolerant until it's been automated and until that automation's been tested. If those two steps are passed, now you have a really clear measure at to what degree, under what conditions, in what situations is your system fault tolerant. The old approach to doing this was just to build more than one. And as you can tell, that's a relatively expensive proposition. You're easily doubling, if not because of the complexity of managing and distributing work between multiple systems, more than doubling the cost of delivery of services. And that's an expense that most businesses, and frankly some business opportunities, aren't ready to bear, right? If you're building an application and you've set an SLA with customers, maybe it's a freemium product or a product where you've made clear to customers the boundary is that this is a best level of effort, that kind of redundancy is probably overkill, probably too expensive to accommodate. But there are positions in between building only one and having any conceivable thing break, meaning that your application goes down, and building 2 or 10 or 20 as the only approaches to fault tolerance. So I work at AWS, and what we've found when we talk to customers, irrespective of the cloud technology that they're evaluating, the software that they're evaluating, the value propositions they want from this transition are these 6. They want to make it so they don't have to pay for things up front, because when they do that, it forces them to make decisions earlier rather than later, forces them to be able to hold the capital up front for the kinds of business executions they want to be able to provide. They also want things to be cheap. Not only do I not want to pay for it right out the get-go, I don't want to pay very much for it over the long term. And they also recognize that as you go through and learn and improve and innovate and iterate on your systems, that if you can only pay for the parts you're using right now, you're likely to save quite a bit. And in many cases, the slowest part of these systems, the most time-consuming event, is procurement or provisioning or waiting for things to get shipped over the mail. I mean, even if shipping is free, it still takes days, and days are time, and time is money. So building a system that is totally self-service, that you need no permission from us to be able to build is very, very valuable. You also, as a result of the combination of those two, want a system that allows you to scale up and down. The ability to have more infrastructure when you need it and not have that much infrastructure when you don't. Being self-service and being able to change on demand gives you the ability to get into market around opportunities much more quickly. So we're talking about fault tolerance. The interesting bit is that fault tolerance demands and can consume all of these benefits, right? High availability, building extra copies of infrastructure, that is a capital expense. We want to build fault tolerance into our systems in such a way where we don't have those capital costs. We want our backups to cost as little as possible. We want disaster recovery to only cost me money when I'm in a disaster instead of all of the time forever. We want fault tolerant applications that are easy to deliver, not hard to deliver. So those benefits for cloud also map pretty closely to benefits for high availability and disaster recovery. So the AWS Cloud, this infrastructure available on demand, lets you throw a shadow that's bigger than you are. You have access to resources you don't own, and you have access to them on demand. You can construct a second copy without paying in many different ways for the second copy. You really only pay for that duplicate, for that overcast of your basic system when you use it, when you need it, and we'll show patterns for how that works. So we've also talked to lots of enterprises, lots of large-scale application developers that have read the white papers and they understand how to do HA. They know the algorithms that HA depends on. They understand the best practices that exist. They just found it fantastically expensive to exercise those patterns. They found it too complicated, too much work, too many of my people invested, and those are all trade-offs between building something that's more highly available or building something that has more features that my customers have asked for, right? And so if you have this very high complexity, very difficult to implement sets of approaches for HA, you end up making a trade-off, a choice between investing in features or investing in uptime. And it also, if you look at the complexity between kind of building another widget on the front of your web app or building another layer of application deployment, it's probably actually easier to build more systems than it is to make systems robust, to make them highly available. We think that not only has AWS added a lot of value in this space, but AWS together with RightScale can reduce the cost and the complexity and the expertise required to get to very best-in-class, best-in-environment, highly available fault-tolerant systems. So AWS has built and approached the market space following two different strategies. So some services, let's use S3 as an example. S3 is designed, if folks aren't familiar with that, that's the object storage in the cloud. It has 2 trillion objects in it. It's real big. S3 is designed to serve all of the data for this thing, you may have heard of it, called the internet, kind of a convenient location to put zeros and ones. S3, we are in charge of the fault tolerance and the availability of that service. So when you put to our web services API, we've done a whole myriad of architectural steps to ensure that those puts are highly available, that the API that you use is available, that the storage that you store to is available. It's designed for 11 nines of durability, that the service of reading that data off is highly available, that the control tools are highly available. Amazon includes that complexity and reduces your exposure to the complexity, frankly, by just giving you access to that service. That also means that we designed and chose the degree of fault tolerance. It is 11 nines. We didn't choose 7 or 64 nines or whatever it would be. We made a choice based on what we heard from the market and said, this is the degree of availability we'll provide as a service. There are some applications, and we've heard from lots of customers, that they'd like more flexibility. Their system needs to be even more durable than that, or they can't afford to pay for that. They want it to be slightly less durable than that, or they're doing it for test. They don't need any durability at all. So a smaller subset of the systems, EC2, your configuration in virtual private cloud, a couple of features in RDS databases, they allow you, the user, to select the degree of fault tolerance. So we have customers that have used EC2 to construct the servers they use for their website, and they'll put one in every one of our distinct availability zones. That's over dozens of copies of the same system. By math, that's more available than the S3 system in a single region. So they dialed in. They chose exactly the degree of availability that they want, and we gave them the flexibility by giving you granular individual building blocks to dial in the degree of redundancy that you want. So we've built and provided exposure for redundancy at each of the different layers of the stack. There are redundant geographical locations. If a whole geographical area were to fail, we have a redundant tier for that. We have facility layers that allow you to have access to multiple buildings worth of systems. We have networking faculties that allow redundant deployment of network systems. We have configuration and operating management and deployment and resources all the way down to the individual computers that are redundant. We built services for that. And we found that while we have regions and availability zones, and we have networking tools, and we have the raw compute power, that management and configuration part, that controlling and instrumenting and governing and delivering a system, that RightScale adds a lot of value at that tier in the architecture. And so we think that there's very much a better together experience for our users by combining these two systems to have a higher degree of control and a higher degree of visibility into the configuration and governance of their system. So a couple of definitives. Fault tolerance is making it so that if something breaks, it still works. High availability is making it so that it doesn't break, and even though individual building blocks that are used to make it up may fail and destroy themselves, in general, the application is ready to do work. And disaster recovery is what you do when those first two steps don't work. And so businesses that are experimenting and then implementing and then depending on highly available business continuity, they need approaches and patterns at each of these three tiers. They need to be able to recover from disasters even if all of their best laid plans go to naught. They still want to raise the availability of systems. If you're using A DR approach, a couple of numbers and values that get used are, the recovery time objective, how quickly do I get back to service, and the recovery point objective, as of when is my data consistent when I get back to service eventually. And so the trade-off between the two, the balance between those two, you're typically having a third item on this chart over on the right that says money. You figure out what's the value of what degree of quickness in terms of recovery time and recentness in terms of recovery point that you'd need for your application. So high availability and disaster recovery approaches and technologies are on a continuum. Some of the tools and the systems that you use to make it so a system never breaks come in rather handy for recovering systems after they've broken. We've really built, and I think there's this core concept, and we showed it back here when we said availability zones. By abstracting the difference between geographical regions and the facilities within those regions, we've created a pattern called multiple AZ, or multiple data center. Really straightforward if you are good at negotiating contracts with colos to set up the relationships with more than one colocation provider and then create data linkages between them that are of effectively unlimited bandwidth. We do that ahead of time for you on your behalf transparently. So you get multiple data centers in each of our regions, you can distribute workloads across them, and those data centers are designed to be fault independent. So in all sorts of different layers of the stack, you're taking advantage of the 5 availability zones in US East, the 3 availability zones in Japan and US West 2 and Dublin and Eastern Oregon, right? Each of these different regions themselves also represent a failure locus, an island of information, right? So you can do some pretty awful things and have, a giant Nordic monster come out and eat Ireland and destroy it, and there's no longer any of those 3 availability zones. There's still 8 other regions around the planet that can have your data, that can have your applications, that can be deployed. Our CTO, Werner Vogels, very smart guy, and is exactly not wrong when he says everything fails all the time. At the scales that we operate, the current standard for that is when Amazon.com was just over a $5 billion business in 2003, we had some computers. We had that same number of computers every day in 2013. So racks and racks and racks and racks and racks of new machines go in all the time. And that at that scale, there are hard drives that are being failed out of the system on a minutely basis. There are thousands of those systems that break around the planet all the time. And they back the services that we just got done describing as highly available. So how do you make it so that when individual parts break, that the services don't die? You have to have an automatically scaling AZ distributed architecture for deploying a given piece of infrastructure. So patterns for that, patterns for high availability. First, and the kind of obvious bit, if it takes more than one thing to make it so that if something fails, your whole system doesn't fail, you really can't have a single point of failure. And that's an easy, that we've been saying that same word for about 6 years. It's not that complicated. And it's harder the further down into your stack that you go. So most of us, I'm assuming more than one of me, have gotten to a place where you're running more than one web server. That's not so tough. If it's a PHP web server or a IIS web server or a Nginx web server. Each of those different services, they tend to be stateful or stateless, but still able to accept a distributed workload. Application tier tends also to be able to do that easily, but databases can be complicated. So Amazon went out and built our own service, and you can build a service just like it using Amazon's building blocks to distribute databases across availability zones. So one customer that used some of these services, CBS Interactive. So highly available web application, millions and millions of visitors a month. Together with RightScale, they deployed a service that allowed CBS to build this application, deliver it into their users, got all of the visibility about usage, cost, availability, frequency, how often were individual building blocks failing or dying, so that they could make a constant improvement in their decision-making process around should we increase the redundancy in this system based on the current rate of failures in the individual building blocks that back up that system? It also allowed them, without too much headache, and we'll show some techniques for that, to deploy this in a multi-regional way. Amazon's regions are designed to be these independent islands of infrastructure, and so there can be some complexity in moving data and moving designs and moving VM images and other kinds of pieces between the regions. We're adding tools for those all the time. We've just added the ability to move virtual machine images called Amazon machine images from region to region, but even that takes the amount of time that it takes to transfer data across the internet. So we have some patterns for moving things even faster than that. So a great example, deploying that architecture, the system for CVS, is designed around this multi-zone, highly available setup. So you use DNS to address multiple load balancing targets. Those load balancers distribute work to application servers or web servers, and those communicate back over one of our availability zones to a master database. And you can run that master database on standard EVS. You can run it on provisioned IOPS EVS. Allows up to 2,000 IOPS per volume. That's up to 16,000 IOPS on standard instances, up to 32,000 IOPS on cluster instances. And if you have a system in another availability zone, you can run that on the same storage types. You can run it on different storage types. You can mix storage infrastructures to get to a place where even if whole service systems have problems on our side, you're still fault tolerant. So that subdivision across AZs drives a really significant benefit. If you lose the whole left side of that chart, there isn't any part of this system that's only sitting on one side. You still serve traffic. That means a whole data center fell offline. You also can have any one of the parts of this application fail. Note that there are multiples of every one of the components. There are multiples of the IP addresses and the DNS registries and the load balancer instances and the app server instances. Each of those pieces are in multiple. Now, an important little thought experiment. Let's say we're going to divide a system into two pieces. How much load can we deliver into just our two instances? The right answer is about 45, maybe 48% if you're real feisty. The reason for that is if you lose one, the other side has to hold the rest. Now, if you have 10 instances that you deploy the workload across, now you can load them much hotter. If you lose one, you only have maybe 10% or 9% to redistribute across the fleet. So Amazon's built using very, very small building blocks will allow you to run instances as small as 613 megs of RAM and a fraction of a core. We have virtual machines that cost pennies an hour, and if you run them in our spot market, you're talking tenths or hundredths of pennies an hour to run servers. And the reason that we focus on these small instance types is so that you can afford to distribute across a large number of instances so you can have a high degree of utilization. If you just use two, you can't load them that hard and still be safe in your designs. Another tool that we've released in our virtual private cloud is elastic network interfaces. So if you have external systems that depend on specific IP addresses, if you want multiple layers of security using VPC network ACLs or subnets, you can use elastic network interfaces to create instances that participate in multiple Amazon networks, that can span those networks, can inspect packets that move between those networks, can move IP addresses and, in fact, whole interfaces. So imagine the NIC being picked up out of the instance and flying over onto another instance. Allows you to create systems that follow the same kind of network structure rules that are maybe present already in most data centers. Yeah.
Can you go back to the previous slide?
Yeah.
So in this diagram, you show that IP address being addressed to two of the load balancers.
Mm-hmm.
Is that possible in AWS?
It's possible with the combination of AWS and RightScale. Yeah. So the question was, it shows an IP address being addressed to multiple different servers, in this case load balancers, in US East 1A and US East 1B. The DNS holds an A record. We have a service called Route 53 for DNS. And DNS allows an A record result, an IP address result, but is typically held as an IP address, allows us to place a CNAME in its place. So now I can, what appears to be an A record, a zone apex record, like I would go to imawesome.com instead of www.imawesome.com, that can render down to a fleet, multiple instances, multiple load balancers. I can also use DNS to do health check-based round robin on multiple instances, latency-based round robin to go across multiple regions. I can also do weighted round robin if I want to bleed traffic on and off individual sets of machines. Very powerful setups for DNS and addressing.
You don't get so typically DNS have issues in terms of their TTL and all that stuff. Mm-hmm. Is that also taken care?
Sure. So an interesting component of the Amazon Route 53 DNS service, we host and manage the DNS fleet across all of the distinct regions. So when you do a change to DNS configuration, say you say this CNAME points from this machine and now instead points over to another machine, or I change the routing rule, or not the routing rule, but the weighting rule from one IP address to another address, we set that at 60-second resolution globally across all the regions for changes. So very, very low functional TTL internal to our systems. Now, external systems have their own adherence, or frankly lack thereof of adherence to the TTLs that DNS set. We allow you to communicate your TTL, but outside ISPs have to observe that or not. Mobile providers, third world ISPs, distant ISPs from the US, they tend to cache things for longer, and DNS ends up holding those buffered results. So customers will have an old IP address or an old DNS name. If you use Route 53, the DNS system, to hold zone apex records, we're supplanting a CNAME instead of an A record name. So what gets cached out at DNS is a CNAME. So that means you have the flexibility to change out which specific machines happen behind, even though the TTL hasn't been observed. Pretty cool abstraction that's present there. So if high availability is about distribution across availability zones, about subdivision of workloads into multiple nodes, disaster recovery often is data-centered. How do I get the data where I need it to be? How do I move it quickly enough? How do I set a schedule for that? Amazon's built a pretty significant number of partnerships with the existing data backup and data archival software providers, but you also have tools for systems that are deployed entirely inside of cloud to move data between our regions, to replicate that data. And it's, as you look at practices and patterns for this kind of work, in many cases, the places where systems like this fall down are not that you couldn't do it once or twice or 6 times. It's that it's not automated enough to run every time, that it doesn't work independent of your attention and focus on it. So we really expect from a risk mitigation and from a planning standpoint that automation and building automation into those processes is totally critical. So your automation itself, if it's something that got done by one guy, it's all API code that sits in his own private little PHP library in the corner and he hasn't taught anybody about it, it's not just enough that you have something that you've tested and maybe it works once or twice. You have to document that, communicate it inside of your organization. And if you're using centralized management tools, RightScale being a great example of that, those interfaces show and expose what is the pattern. Let's audit our pattern for disaster recovery. Let's audit the structure of what we're using for high availability. Let's inspect what we expect and ensure that we've built a system that follows everybody's current understanding of how those tools are supposed to work. We also really recommend testing like crazy. Test for fun. I like the new shirts that are out that said I built an app and I broke it just for fun. We have a pattern that we've started doing. Let's make this sort of thought experiment. Because of the access and governance control that RightScale provides, I can give this half of the room access to my system, and you guys all have the same access into, say, a staging copy of our production environment. You can do whatever you want. In this side of the room, you have the same level of access to our staging environment. This team, you're the bad guys, and you should just go break those systems. Log in, cause havoc, delete servers and delete storage and break queuing systems and destroy network connections and alter subnet ACLs and change all of the different structures. This team, you go through and you fix all that stuff as fast as you can, just like you really would in the middle of the night in a real sort of production event. And then a subset of this team, maybe it's the front row, you guys take notes. And if you do this together as a team, both sides actually get benefit from each other's creativity and investment in the exercise. If you come up with some particularly sneaky way of breaking the system, or you come up with a very easy automated way of fixing some kind of breakage, those practices as a DevOps approach to solving problems make it so that the first time something does something you don't expect, you have a little more experience with that. You have a little more familiarity with not only your tool system, which maybe you've only been using to deploy or to build and not really to operate and manage, but also a little better understanding of who on your team has what skills and is familiar with which parts of your system. So there's a human component to all of these approaches as well. From a structure standpoint, if you're looking at the kind of DR tiering, we have most customers, most of the time, are doing this thing you've heard of called backups. Backups are great. I really recommend you take a backup or two. Backups are useful. I don't think anybody's going to get fired for taking a backup. The typical problem with your average backup is they don't get taken very frequently. They tend to allow a pretty far RPO. They tend not to deliver the kinds of high availability that we've been talking about. They really are a disaster recovery option. Amazon's had however many gazillions of backups delivered into S3, and now a new service, Glacier, allows us to deliver archival of those backups at a penny a gigabyte. But as you move up the stack, as you get to more and more active patterns, what are some structures that make sense? So if you're doing cold disaster recovery, you have really only active delivery inside of one of our regions. We really think of the regions as, for most businesses and most applications, as if you're going to pick up and move to another region, that's kind of a reaction to a disaster, rather than distribution across regions as the initial first step. Of course, you would automatically do that. There's extra complexity that comes with a multi-regional deployment, typically extra cost. And so doing a multi-AZ design is so trivial, is so straightforward, is typically so easy for most systems. We recommend most customers start there. So your cold disaster recovery approach, you're really only taking the stuff from S3, the data in your backups and your snapshots, and migrating, moving that stuff over to another region. That pattern is just limited by how much data you have and how much you move. We also have seen lots of customers do this and then not ever actually try a restore. I really recommend you actually try a restore. They help. Another pattern, RightScale calls this warm DR. We call it the pilot light. So if the whole point of this is that you can build applications on demand, if you just replicate from the master database over into a remote region, you can even replicate onto a server that's smaller than the original. It doesn't have to serve any read load at all. It's just the right target for replication. If you leave that instance running all the time, now the more flexible, typically faster to deploy, typically more portable systems that aren't as data heavy as your databases, the app tiers and the web tier and the load balancer components, those can be deployed on demand when there's a failure. And if your application really does require a much larger database, the amount of time that it's going to take to spin up the app servers and the load balancers and other pieces, your database can typically restart at a larger size. AWS's RDS, or if you're hosting databases on EC2, that's a simple stop, modify image, I want it giant, and play. Yep?
RDS doesn't support cross-region replication yet, does it?
Correct. You're not replicating across regions with RDS, so that's a great place where RightScale's tools have made it easier to do this kind of pattern. They're hosting a structure for deploying MySQL that does allow cross-regional replication. So that's a little better setup. The question was, RDS doesn't allow cross-region replication, so how does this pattern work? And we say it's a pattern that's enabled by the partnership with RightScale. So if you go to hot disaster recovery, you're running all of those systems in the remote region, but you're not really sending traffic to them. Maybe, particularly if they're auto-scaled, maybe there's a smaller number of application or web servers on our side to reduce cost, and you'd scale up when you create the DNS record or point traffic into the production system. That's certainly much faster, and its recovery time objective can be set at a lot lower rate. Your RPO should be 0 if you're replicating between the regions. The worst case is you've gone to asynchronous replication and now the sync is out of sync. But typically you're talking minutes. Another important ingredient in a lot of these patterns, if you are replicating across regions for the database tier, using WAN optimization, there are a couple of different products that function there. Riverbed and Cloud Opt and several others, where you can compress and deduplicate and WAN accelerate for transit across our regions and keep that sync delay lower. That pattern gets you to running more quickly, reduces RTO, but I'll tell you from practice, we're seeing more customers looking at this model if they think of what they're doing as disaster recovery. Here, you've started to fold over into the kind of high availability side of designs. And then full highly available across region designs, you're looking at using DNS, latency-based routing, as well as load distribution across our regions. So very powerful, very much the best practice for the most mission critical, most advanced applications, but certainly a place where it's possible that that's going to be a relatively expensive approach. This also, if you're built this way, probably easier than for patterns like this where you're very dependent on the sort of specific replications between regions. You can even extend beyond AWS services, use other private providers, use other public cloud providers. That's one of the big advantages of the RightScale model, is the capacity to accommodate more of those resources. So in a lot of ways, this is the same view. If you just squint, that looks the same as that picture, right? It's just that we're talking about regions and not availability zones. So a lot of the monitoring, a lot of the evaluation of performance, a lot of the optimizations in these systems, they tend to match up. The big difference is going to be the latency, again, between the regions. And there are lots of different drivers for which region you'd choose as a failover target. In the United States, that's relatively straightforward. We have East Coast and West Coast environments, but some folks have customers that don't want to put data in the United States at all. Some folks have customers that will only ever put data in the United States. There are lots of rules there. So AWS has provided the high number of global distinct regions: Sao Paulo, Tokyo, Ireland, Sydney now, so you can really go on to several different continents if you're so engaged. So we also do think, as per the question earlier, DNS becomes ever more critical the more global your system becomes. So really expect for most customers, like some work we did together with Coupa, that DNS becomes pretty critical. So there's another presentation today that's very specific to the work that got done together with the Coupa company, and what they worked on is they tried to establish an SLA, and they looked at the AWS SLA for availability for the EC2 API. They said, this isn't the SLA we're delivering to customers. How do we keep our SLA when your SLA isn't the same as ours? One of the unique things about the way AWS is built is because you're procuring individual components, individual infrastructure pieces from us, you can build to any SLA. You can span across our regions, you can span across our instances, you can span across our services, and get to a place where you're delivering at a far higher rate than the individual building blocks we deliver. So what does this stuff look like if you look at it in the RightScale dashboard? If you're looking here, you see compute hour consumption in both East and West. We have a database master, that's the top line, running in East, and its slave running MySQL 5.1, that's running in US West. Each of those items are shuffling data in between the two of them. You also have a slave in the East. That's so that if you don't use West, this is the pilot light pattern, if you don't fail over all the way to the distinct region. Is it a regional outage? You typically have a lower latency, lower turnaround failover if that happens inside of a given region. And then our web tier is online, green box, in US East, and then offline, red box, in US West. Ready to start, already configured, has all the right information. And if you look at the difference between the amount of time, say you push 6 new updates to that Rails front end on US East, those updates are captured in write scripts. They're provisionable on demand when the instances start rather than baked into the bits of an Amazon machine image. So if you had a disaster and you needed to get the most recent build, you'd either have to wait for the copy of an AMI to happen across the regions, or because you're using RightScale, you're able to deploy based on the newest code, have those instances run through their boot time scripting and get configured in the up-to-date way. So pretty powerful benefit of that kind of on-provisioning time configuration management. So you also, in this environment, because of RightScale's price governance and price cost management, you have a view into the monthly cost projection for each of these services, a better look at how much your HA or DR processes cost. So we talked about this a little bit. Using dynamic DNS or Route 53 DNS is a very powerful tool for moving those pieces around. Also really strongly recommend direct testing of your slave to master or master to slave rotation promotions for databases. We talked in this through examples using relational databases. I'm the author of the MongoDB on EC2 white paper. This kind of stuff can also be automated in NoSQL database systems. There's quite a bit of process. We have, as a practice, what we see most successful and sophisticated customers doing is they automate the entire process of doing disaster recovery, but they leave manual the process of initiating that automation. You don't want to just pull the trigger on DR without someone being in the loop. And that depends on whatever your business rules are around the amount of time you can tolerate for downtime, whether that's 30 seconds or 5 minutes or 5 hours or 5 days. So we've also heard from a lot of customers that data and data gravity and data storage is a significant impediment to their ability to get to highly available designs. So we released a service called the Storage Gateway. This is a virtual machine image that you run on premise, sitting on top of storage that you have locally, and we'll replicate that storage to S3. We expose from that on-premise connection an iSCSI connection type. So you don't have to learn the S3 API. Your applications don't have to be compatible with S3. You just talk iSCSI like all the rest of the systems in the world, and we manage replication of that data to S3. The unique part of this is certainly if your data center on premises fails or if you have a hard drive error that's local, you can create another storage gateway virtual machine and download your data over again from the cloud. That's kind of the whole point. You wanted a backup. But if you need access to that data more quickly, rather than those objects being stored as S3 files, where you have S3 permissions into individual objects, we store them as EBS backups. So you can create new servers, new EC2 instances, attach those EBS volumes to those instances as snapshots, and right away have access to the data that you've backed up. The storage gateway allows what's called a cached mode, where local storage is just the most frequently accessed or most recently uploaded data, and up in the cloud is up to 150 terabytes of backed up content, and that's per storage gateway. You can have as many storage gateways as you want. So using that model, you can take even potentially underperforming, old, unused NAS systems, inferior sort of ancient SAN technology, broken stuff that you've got around, and extend the performance of that by connecting it to the cloud, by having it operate at a scale beyond which it was designed. So very powerful tool. You can also, if that iSCSI connection type is valuable and something that your design pattern you'd like to see replicated elsewhere, you can also run the storage gateway virtual machine on EC2. So you can start it as if it's an instance. a very powerful way to get access to storage. So, no problem. RightScale makes this kind of deployment where you're moving from availability zone to availability zone, where you're moving from region to region, much more straightforward because of the multi-cloud image model. By constructing images that run scripts at start times so that the instances are configured exactly the way that they're supposed to be, irrespective of the target for those launches, you're able to deliver availability across cloud resources, across regions, and across providers. So we also allow you very, very nuanced configuration of the individual parts of the server that you're deploying, not only the processes and the applications that are running, but the DNS that it uses, the block devices that it leverages. So there's no stone unturned. There's no part of your server that can't be automated. You should be able to deliver a system that's designed not only to just deploy one server the right way, but your entire stack in an aggregated fashion so that you get the databases where they're supposed to be and the security groups configured how they're supposed to be configured and all that. From a cost standpoint, now a lot of the driver for which one of these approaches that you use is cost driven. Clearly, if we all had an infinite amount of time, we had an infinite amount of budget, we would just make everything run everywhere on every computer there is, and by gum, it wouldn't go down. But since we all live in the real world, you do in fact have to choose how much it costs. So you have several different looks, like that kind of multi-region backup, but cold, inactive, is almost half the cost of a hot backup running in a remote target. It's twice as many servers that are running all the time. But the interesting one is that pattern in the middle, where for most of the recovery time benefit, almost all of the recovery point benefit, at really only about $1,000 extra a month in this sort of implementation, you get most of the benefits of the right-hand column at nearly the cost of the left-hand column. And that's the spot that cloud made available because you have that on-demand access to the web and app tier and load balancer tier of your infrastructure. That's the place where lots of businesses are saying, okay, I've really tangibly, really measurably improved my HA and DR pattern at a price that's just a fraction above what I was used to paying. So best practices, sort of basic outage proofing, have more than one thing, place them more than one place, test that they're in fact there, certainly replicate your data across zones and across regions, but also monitor that, inspect that you're actually doing it, run recoveries on a frequent basis to ensure that you know what it is your systems do when you trigger these kinds of behaviors, and then look at potentially new kinds of software platforms, right? Not relational databases have their own complexity around these models. Some of the newer NoSQL database systems have better options for high availability, for disaster recovery patterns. We also recommend looking at all the different storage services that are available, both EBS, provisioned IOPS EBS, S3, ephemeral disk, as well as external partners like Zadara and other pieces where look for the storage device that gives you the flexibility that you need at the price point that you need to deliver on these kinds of patterns. And please, please test everything. Destroy your computers. Cause them incredible violence. The Netflix folks, Pat released this software called Chaos Monkey. It's a simple device for destroying individual instances at random. You dial in exactly how much destruction you want. I think that's a great first step, but I really recommend people go to that next step to the pattern we described as game day, where you're really letting your engineers be as creative as they want to describe what it looks like when all of your software gets misconfigured on first launch, or what does it look like when an automated build doesn't work how you expect. Those kinds of pieces. So really appreciate everybody's attention. We're here and available, Amazon folks as well as RightScale folks, it is their conference after all, to field your questions, but I'm hoping that there are a couple things I can answer around HA and DR on AWS and RightScale.
Good morning. Would you mind describing a little bit specifically how RightScale helps in the gentleman's RDS question as far as replicating data across regions and so forth?
Sure. So RDS is a hosted managed service for databases from Amazon. So we have a software wrapper that controls computers and storage and all sorts of bits to make it so that you have access to a database. RightScale doesn't extend that service. They replace it. So they run a write script that configures EC2 instances to run MySQL or to run Postgres or to run other database applications. And their configuration of those databases also allows cross-regional replication as a feature. So it's not a change to RDS. They're running databases straight on EC2.
And from a future perspective, can you give any insight if Amazon is planning to do that with RDS?
Sure. We don't speak about sort of future releases. We're releasing at about a feature a day at this point, so it's hard enough just to keep pace with what we're actually doing. But we are always listening to customers, and we always want to make things better than they are. So I don't think there's anything that's off limits. Question in the back? Thanks for the good question.
I just have a follow-up about that replication across the larger geographic regions.
Mm-hmm.
So let's say you need to do that in a DR case. You flip to the other region because of an outage or natural disaster or whatever.
Sure.
And
I
you
prefer
flip
Godzilla,
over there,
but
and then you're running active on that database and changes are made. What are the considerations to getting back?
Sure. It's an interesting pattern, and we've seen it a bunch of different ways. If you're running databases and data services on premises, and you're looking at using Amazon Web Services as a disaster recovery target, we recommend that you recognize that's also a whole bunch of the work towards a migration path. So happy to have you come test migration by doing a disaster recovery failover onto AWS. For the failing back cycle, the biggest driver that we're looking at with customers is identifying and scheduling the time, looking at and evaluating for their current actual data size, the rate of growth in their data size, what is the transit rate, and actually practice the transit rate of that much data from region 1 to region 2 so that you know, okay, we accepted a data loss over here. We don't want to accept a data loss when we fail back. So the pattern for that is about, typically you take, say, if you're going to use MySQL, you take a MySQL dump, say that is an hour or an hour and a half to transit over the wire because it's a very large file, right? And now you enable extra logging on MySQL so that you have the full T logs of every one of the functions that occurs. So now, once that whole database is transited and restored, and you can test that it's in the state that the other side was in, the clock is still ticking, and you're still taking writes over here. The next transit that you do is only those next transit logs, the T logs, the next operational events that have happened. You take just that back up. Now that should be a smaller file. Maybe that gets you down to 15 minutes, and the restore takes 6 minutes. So you've got that 26-minute window. Once you do that 3 or 4 times, you should be able to shorten that operational window down to 5 minutes or 3 minutes or what have you. You end up doing that transit 2 or 3 times, and then at the last minute, typically you'll enable caching for reads and disable writes or route writes to the new database so that you'll take the 30 seconds or a minute to flip DNS over to the other side using Route 53, drive new writes to this source, cache reads locally over here, and then move DNS over to the other side to start serving reads from the new copy. So mostly it's about shortening. If you did that all as one step, you're taking a 2-hour downtime, right? And that's the last thing all of us want to do. Yep. Mm-hmm. Any other questions? Open season.
Would you mind briefly going in again or showing the slide again in regards to that new storage, local storage instance, and elaborating just a little bit on the complexity of that, just a little bit?
Sure. So it's about the easiest thing to build in the history of the world. It's so great. You download a less than a gigabyte virtual machine image that runs on Hyper-V or VMware. You install that virtual machine on Hyper-V or VMware, And Hyper-V or VMware will have access to storage that's a part of the virtualization pool. You assign that storage in 1 terabyte units as individual volumes connected to the storage gateway. So the storage gateway then exposes iSCSI, and it writes through the iSCSI connection down to the local storage. You also provide an additional, typically 20%, 30% of the local write to storage as working cache. So it writes to both of those targets, and then the data that's in working cache is written to S3. Right? So S3 connections, that happens over an SSL linkage. You can WAN optimize that connection if you're so inclined. When you do those writes, you have the option of enabling at the storage volumes cache mode or direct mode. If you use cache mode, you can over provision against the local storage and write even more data through to S3, up to 150 terabytes. If it's in direct mode, you're at 12 terabytes local and remote. Those volumes are EBS snapshots, just exactly the same as if you had written that data on an EC2 instance to an EBS volume and then snapshotted it to S3. So it is stored in S3. It's 11 nines of durability like S3. It's not going anywhere like S3. And can be deployed to any of the availability zones in a region as an EBS volume. Right? So that data is also accessible without volume restoration directly over the storage gateway link back to your storage. So you lose disk number 2 of those 4 attached disks. You go into the VMware portal, you go into the little web interface that it exposes and say, restore that disk for me, and it does it. It's really nice, really tidy. Go ahead.
It's a little bit beyond HA. Not sure if this is the right forum, but let's
open season.
For the applications of very heavy data usage, like streaming applications, right? Mm-hmm. We have seen limitations on, let's say, if the load balancer can handle 2 gigabits per second, something like that. I'm just throwing up a number, and your application can also do 2 gigabits per second application server, right? What am I load balancing now?
Yeah.
So this is the number I got from AWS, that 2 gigabits per second is the number. You cannot go beyond this.
So that's wrong. I built the live streaming infrastructure for the NASA Curiosity rover landing. So all of the high-def video streaming for watching when the dude with the mohawk said, "Woo, we landed," I helped design that stuff. So we were serving nearly 8 terabits a second of that video. So that takes multiple elastic load balancers and multiple instances behind those. But that had been thousands of load balancers if we were doing it at that scale. The elastic load balancer auto scales. So at the beginning of load balancer construction, because we don't know what traffic you're going to deliver to us, we start on a relatively small set of systems, and we observe your traffic load. And just like your EC2 instances, we auto scale the load balancer to accommodate load. Now, if you're using like HA proxy on an instance, there's only so much network connectivity to a single machine, so it will maximum out. But the elastic load balancer auto scales. It can grow to accommodate additional network throughput. You just have to provide it that throughput. So if you are a customer from support, if you're using the premium support services, which I really strongly recommend to everybody, it's a great experience. If you know you're going to deliver a high amount of load to a load balancer and you want to test it, or you're going to fail over from like a blue to a green deployment, you have a whole stack of infrastructure, you can send in a ticket to us for a pre-warming or an increase in the maximum performance of your load balancer ahead of time. That's something you can coordinate with support. Very straightforward practice.
So the data for going through from the storage gateway to S3, that is encrypted but not compressed.
It is encrypted in transit by SSL, not compressed, but you could compress, right? So if you write in over the iSCSI connection compressed data, it's compressed data that's flying over the wire.
Of course, but by
But
itself,
we
you
don't
can
do the
have
compression on your behalf. That's
not
correct.
even SSL compression.
No. Nope. It's just raw bits flying back and forth.
And it's only runnable on Hyper-V or VMware. I can't.
Today it's just Hyper-V and VMware.
So
That's
I can't
correct.
run it in a like a Rackspace instance and connect back.
You can buy a computer from them and have them put VMware on it, and then you can run it right there.
I'll keep that in mind.
Yeah.
Anybody else? Last call.
Thank you, everybody, for the good questions. Happy to field any other questions after we're done.